So please take the rotation operator and take this n cap as x cap and proceed. So this will be your rotational operator about x-axis. So similarly, I need ry of 5 and next rz of 5. Next, take about y-axis. Please do it yourself. You will get confidence. Ry of 5, that is e raised to minus I 5 by 2 sigma y. And the next, about z-axis, that is rz of 5, e raised to minus I 5 by 2 sigma z. Please get those three rotational matrices. So this is just substitute sigma y here and tell me what you are getting. This is a cos 5 by 2, 0, 0, cos 5 by 2, and this is a minus. Here we have I sin 5 by 2, multiply with the sigma y. That's why this is a 0. Here minus I is there. Here we will get sin 5 by 2. And here iota is there, and here minus iota. So here iota is there. So what you will get here, minus sin 5 by 2, and this is a 0. So I hope you got this. Cos 5 by 2, sin 5 by 2, and this is minus sin 5 by 2. Wait a minute. Sorry, this is plus and this is minus. Please check, cross check whether you are getting same or not. I don't know any issue because I forgot to restart the server today. I forgot. I think morning also we didn't restart. Let me check what is the server status. I think it is. Its RAM is full. I think. No, it's 5. Okay. But anyhow, I think now it's going on smoothly because actually we have to restart, but I forgot. Okay, anyhow. So please check this. And similarly, Z. This is important for present discussion. Please do this properly. Again, cos 5 by 2, I minus I sin 5 by 2. Make it fast. So this is cos 5 by 2, 0, 0, cos 5 by 2. It's a simple matrices. So very easy algebra. So this is I sin 5 by 2 and 0, 0 minus I sin 5 by 2. So I think you got here e raised to I 5 by 2, 0, 0, e raised to minus I 5 by 2. Check whether I think this is minus and this is plus. Please check your answers. Right. Now stop. So here I am taking this is rz cap of 5. This is the rotational operator about spin rotational operator about z axis. How much we got once again? E raised to minus I 5 by 2 and 0, 0, e raised to I 5 by 2. Wait a minute. But unfortunately in quantum gates, while we are designing this quantum gates, while we are operating this quantum gates, we won't take this operator. And we won't take like this. The reason you will understand slowly when I am introducing that quantum gates, you will understand. Just to keep that point in your mind. So then what you are doing? See, here I want to add some more phase called global phase. So wait a minute. So once again, this point is very crucial, but please remember, again we will discuss this, but remember, once again. So what I am doing is, here I am taking this operation, I am taking this operator, 2 times I am operating. That means just I multiply 2 times. E raised to minus I phi by 2, 0, 0, e raised to I phi by 2. So one more time I am taking e raised to minus I phi by 2, 0, 0, e raised to I phi by 2. Instead of operating 1 time, I am operating 2 times. Please underline this statement and remember. There is a beautiful concept behind this. What is the reason? We will explain. So if you multiply, what you will get, please check. Here I think you will get e raised to minus, 1 minute. What you are getting? E raised to, is this right? We need to get a 1, 0, 0, e raised to I phi. We need to get 1. Where is that 1? Oh. Here we need to get 1. Please check whether they have taken unitary of this. No. This is the row, column. 0, 0, and e raised to I phi. And where is the 1? I'm sorry, it's somewhere. Oh, sorry. Got it. 1 minute. So here what I'm doing is just adding a global phase. So why you are adding like this, you will understand later. Please wait a minute. So what is the meaning of adding a global phase? Just to multiply the entire elements, that means all the elements with 1 more e raised to I phi by 2. Just multiply. Earlier I have taken as a small wrong thing. Multiply with e raised to I phi by 2. That means I am adding this phase again. So what you will get here, the matrix will become, this is a 1, 0, 0, e raised to I phi. So every element is multiplied with e raised to I phi by 2. Then what will be the change? Operation no change. Only here the change is the global phase, but this operation and this operation represent same. That means operation remains the same. Operation remains the same, but the only change is what? Global phase. But there is a change of global phase. Sir, what is this global phase and why we are doing this? There is a reason. While you are constructing a quantum gates, you will understand. Till then, just wait. So I repeat, this is my rotational operator about z-axis. I am adding some phase, extra phase. That means I have to multiply every element with e raised to I phi by 2. That means I into e raised. I means the matrix, e raised to I phi by 2. Then if you, if you multiply every element with e raised to I phi by 2, here 1, 0, 0, e raised to I phi. So these two represent the same operations, but the only change is a global phase. I will explain that point again, just keep it aside. Now once again, here we have Rz of phi, This is the reason why I have taken phi instead of theta. So 1, 0, 0, e raised to I phi. Everyone? Now I am giving the phi values. Let us suppose phi is equal to 2 pi. Can you please take this and substitute here? Then what you will get? Come on. 1, 0, 0, e raised to I 2 pi. How much? 1. This is I gate, IST, I gate. Next, second one. Let phi is equal to pi by 2. Phi is equal to pi by 2. So please take this. Then we get 1, 0, 0, e raised to I pi by 2. So you can write this as 1, 0, 0 iota. So this is called S gate. What is this? I. What is this? S. Okay. And the next I am assuming one more phi. Phi is equal to pi by 4. Pi by 4. Very important, ma. This is 1, 0, 0, e raised to I pi by 4. So this is called T gate. T gate. And this is S gate. And this is I gate. And if you observe carefully, I can write this as, if you observe carefully, 1, 0, 0, e raised to I pi by 2 whole power 1 by 2. I hope you are observing. That's why this T gate is also called as a square root of S gate. I repeat. See this one, e raised to I pi by 2. So here e raised to I pi by 4. We can write it as e raised to I pi by 2 whole power 1 by 2. So that's why the T gate is also called as a square root of S gate. So finally, here we have I. That means no change. If this is a psi initial, there is no change in the psi initial state, same as it is. And this is called S gate. So what it will do? It will add some phase actually. That is a phase difference only. I hope you know. And this is a T gate, and which is called as a square root of S gate. You observe one thing. Just find S star. S star or S dagger? S dagger. Find S dagger. 1, 0, 0, e raised to minus I pi by 2. Find T star. So this is also one of the gate. 1, 0, 0, e raised to minus I pi by 4. Now you got it out. Sir, earlier sigma x, sigma y, sigma z, head madu, you have not taken dagger because their dagger is the same. But T dagger is not equal to T. S dagger is not equal to S. I hope you are observing. So that's why we have one more extra gates called S dagger and T dagger. T dagger or star, whatever it may be. It's not an issue. Okay. So finally, these are the IST gates. I for identity, S for phase, and T for square root of S. Square root of S. Okay. So one more time I'm saying here. This is our rotational operator about z-axis. Here I am adding some global phase. The reason we will explain later. That means multiply every element with e raised to I phi by 2. Then I got this. So this is my present Rz of phi. Sir, both are same? Same. Same in operation wise. But the only difference is some phase difference is there. So I have taken and put phi is equal to 2 pi. And here pi by 2 and here pi by 4. Okay, come on. Let us discuss one interesting concept. Listen. Now again I am taking about NOT gate. Everyone, please. Here we have, already we discussed a quantum NOT gate. In the last class, you discussed this quantum NOT gate is nothing but Polyx gate. Am I right? Yes, sir. Wait a minute. Polyx gate. So earlier what we discussed is, if it is a 0 initial state, this Polyx gate, it flips to 1. That means 0 is changed to 1, as well as 1 is changed to 0. Wait a minute. Listen carefully, very important. So on the block sphere, what is happening here? For example, if you take a block sphere, wait a minute. If I take a block sphere, so what's happening? This is the north pole, we have 0, and this is the south pole, we have 1. And what this NOT gate is doing, 0 converted to 1 and 1 is converted to 0. That means it is changing 0 to 1 and 1 to 0. So what NOT gate is giving? The NOT gate is giving opposite points. Am I right or wrong? Yes. From this point we can say here Polyx gate. Polyx gate is giving, just please observe carefully, is giving opposite points on block sphere. Very good. Wait a minute. It's a really good point. So we are getting opposite points on the block sphere. That's good. Now let us consider an arbitrary state. Okay. Now what sir is doing? Earlier he has taken a single qubits 0. It flipped to 1. 1. It flips to 0. That means it is changing the opposite points. If you have 1 point, it is changing to opposite point, and this 1 point is, this pole is converted to this pole. That means it is changing opposite points. Now what I am doing is, I am taking an arbitrary state. Everybody know what is the arbitrary state? Yes, already you know. Cos theta by 2 ket 0 plus e raised to I phi sin theta by 2 ket 1. Now I will apply x NOT gate to this arbitrary state. According to this definition, please tell me, we have to get quite opposite point on the block sphere. Then let us check whether you are getting or not. Repeat, here I am checking the NOT gate operation with an arbitrary state. If you take single pure qubits 0, you are getting 1. 1, you are getting 0. That means this north pole to south pole to north pole. So you understand, okay, Polyx gate is converting the points from, points on the block sphere from one side to another side, quite opposite points. So here I am trying for arbitrary state. Now let us apply. Are you ready? My X gate is already, I hope you know this. This is X gate. You remember? Yes, sir. This is my X gate in outer product form. I'm going to operate this on the arbitrary state. It's really interesting. Listen. So this is a 0, 1, plus 1, 0. Operating on cos theta by 2, 0, plus e raised to I phi by 2, sin theta by 2, ket 1. So I hope you understand what I'm doing. I'm checking this Polyx gate operation with an arbitrary state, linear combination state. For single qubits, I'm getting quite opposite points. If I given this point, I'm getting this point. If I give this point, I'm getting this point. This is for single qubits. Now I would like to check what will happen if I take the general state. That means a linear combination. Let us see what got decided. So this is a ket 0. So then you please verify any bra 0 here. Yes. So this and this will be multiplied. You will get 1. That's why cos theta by 2. I hope you understand what I said. And this is 1. Next here ket 1. And check where is the bra 1. Here. Plus e raised to I phi by 2. Sin theta by 2. Ket 0. Try to understand. This is the when X gate operates on psi. Now here we are checking that Polyx gate is a universal NOT gate or not. You said earlier yesterday you said quantum NOT gate. Polyx gate behaves like a quantum NOT gate. Now I would like to check, is it a universal NOT gate? The answer is no. That acts like a NOT gate only for pure single qubits. Pure single qubits. It is not acting like a NOT gate for linear combination. I don't know how many of you got this point. So that's what I'm going to prove. So this is my answer. Let it be 1. Now I'm going to find the opposite point. If I find the opposite point to this, if I get this answer and this answer same, then X gate is universal NOT gate. If both are not same, X gate is not universal gate. Universal NOT gate. I repeat, we have seen this X gate operation only for single qubits. Now I would like to check for linear combination, will it be the same? That means quite opposite points you are getting or not. That's what I am saying. In the earlier classes, I told you theta will be replaced with pi minus theta. Phi will be replaced with pi plus phi. I hope you remember. Those who are revising the notebook, you will understand. Take it and substitute, Babu. Psi opposite equal to, I think this is, shall I write directly? This is a pi minus theta here. That's why sine theta by 2 get 0. Next, e raised to I phi. So take this and substitute. E raised to I pi minus, I am writing directly, e raised to I phi. And sine theta by 2 will become cos theta by 2 get 1. So this is the opposite point. But when X gate operates on the state, you are getting this. Are they same? No. 1 is not equal to 2. Okay. So Pauli X gate is not at all universal quantum NOT gate. Pauli X gate is the NOT gate only for pure single qubits. That is a computational basis states. Not for linear combination. Not for general state. Then what is the universal quantum NOT gate? That we will see later. First, I hope you understand the conclusion. The Pauli X gate. Because both are not same. We are not getting the opposite point. So, Pauli X gate is not universal. Is not universal quantum NOT gate. Quantum NOT gate. Because what is the reason? So here you have taken 0 and X gate, it is flipping to 1 and 1 and X gate, you are getting a 0. So these two are opposite points. But if you take some arbitrary state alpha 0 plus beta 1 and you operated this X, but unfortunately what you are getting here, alpha 1 plus beta 0. Okay, but unfortunately these two are not opposite points on block sphere. Maybe this is some alpha prime or beta prime, something else. Coefficients can be anything now. Because here if you see carefully, yeah, no, same only, sorry. Yeah, same one. Earlier cos theta by 2, 0 become 1 and e raised to I phi. Why I have written this by 2? Right. E raised to I phi sin theta by 2, 1 will become 0. So this is the operation. But unfortunately, this final state and initial states are not at all opposite points on the block sphere. That's why conclusion, Pauli X gate is not the universal quantum NOT gate. Come on. Universal quantum NOT gate. That's it. Okay, so now you have to know what is a universal quantum NOT gate. For that, we have to go to 2-qubit quantum gates. Are you ready? Yeah. Take a fresh page. Put the heading. Please take a fresh page. 2-qubit quantum gates. Quantum gates. If you are following, please attend. Otherwise, don't waste your time. Your time is also precious. Okay. Listen. Right. 2-qubit quantum gates. Ready? So first we have to write the basis states. I think in the last class I already discussed what are the basis states. 0 0, 0 1. Listen carefully, very important. 1 0 and 1 1. So in the binary notation we can write this as 0. Okay, this also I explained, I think. This is the 0 value. And this value is 1, 2 power 0, 2 power 1, 2 power 0, 2 power 1, this is 2, 2 power 0, 2 power 1, this is 3. Okay, so we can equivalently, we can write it as 0, 1, simply some people will write 0, 1, sorry, 2 and 3, or you can write cat notation, it's not an issue. And one more thing I discussed already. Did you remember what is this eigenstate? I think this state is 1 0 0 0. Please remember, very important, 0 1 0 0. Yes, this is 0 0 1 0, and this is 0 0 0 1. And I told you one more thing. If you write all these columns, all these basis vectors as columns, we will get identity matrix. Don't forget this, very crucial. Because if you understand this identity operation, you will understand the gates very easily. That's good. So this is my identity matrix. Very nice. Now here, any single qubit quantum gate is represented by unitary operator. Already you know that. What is that? E raised to I alpha and R n cap of theta. Already we know that. Similarly, this 2-qubit quantum gate. How to write? 2-qubit quantum gate. Listen carefully, please. This 2-qubit quantum gate is represented by controlled, repeat, controlled unitary operation. Controlled unitary operation. So what is this controlled unitary operation? This we call it as CU. C for controlled, U for unitary. Let me discuss. So here we have two qubits, initially A and B. Okay, now here we have this CU operation. I told you CU operation. This is the representation of that CU. This is called a CU, controlled operation. This is the initial state A and B, single qubits. Okay, so this is the representation of that controlled unitary operation. But that CU is given by a matrix. Don't get tension. This is very easy. I2, O2 and O2. That means 0 null matrices. This is identity matrix and this is U. This U is nothing but 2. So now you have a choice. You can't change this I2, O2, O2 and these three things you can't change. But you please focus on this. Now I can take this U as X, Polyx matrix, which is 0, 1, 1, 0. And I can take that U as Z, that is 1, 0, 0, minus 1. And I can take that U as S. I already told you IST gates, S gate, 1, 0, 0 iota. Okay, now see, everybody understand once again. The two qubit quantum gates are represented by controlled unitary operation. So what is this controlled operation, unitary operation? This is the gate, controlled unitary gate representation. So here we have two qubits and this U for unitary operator. This is represented by a matrix Cu equal to I2, O2, O2 and U2. Now I have a choice here for U. I can replace with X. Then I will get a controlled NOT gate, C0. If I replace U with Z, I will get a controlled Z, CZ. I hope you are observing. And if I replace U with S, I got a C phase gate. These are the basic two qubit quantum gates. One is C0, another is CZ, another is C phase. Means controlled NOT, controlled Z, controlled phase. So here I have given a notation only. How it operates I didn't explain. I will explain. First try to understand. Single qubit quantum gates are given by e raised to I alpha r n cap of theta. Simply we have replaced that n cap, then we got all single qubit quantum gates and we changed that angles. Now the two qubit quantum gates are represented by controlled unitary operations. That controlled unitary operation representation is this one, the two qubits, and this is the controlled unitary operation. So this operation is represented by a matrix because every quantum gate is a unitary operator. So that is I2, O2, O2, U2. And now you have a choice. You can replace U with X, U with Z and U with S. Then you will get controlled NOT, controlled Z, controlled phase. Any doubts? Come on. Easy, very easy. Over. Now what textbooks are saying about C0 gate? Wait a minute. Completed? Yes, someone is raising the hand. Yes, Babu, what is the doubt? I think your mic is muted. It is not accepting, Babu. Your mic is muted. Don't keep it muted. We already muted you. No need to worry. I said already, why you are worrying, I didn't understand. No one will listen your voice. No one will listen your sound. Before starting the class itself, all your mics are muted. So we will do from admin side. You personally no need to do anything. Please. Yeah. What is the doubt, Babu?
Sir, from the diagram. Hello?
Yes.
We see that A is not connected.
A?
Yeah, the A vector, it is not connected.
No, I didn't give this output now. Just wait. I didn't give the output now. Output A is as it is. Right. Ready? Now let me explain. So this point of view, this is my personal point of view. It is not in the books. Just remember and leave it. Now, so what is this C0 gate? Once again. So what textbooks are saying? Listen everyone. So here we have two qubits. That is one is A and B. So this is A. And here we have this C0. C0 means U is equal to what? X. Are you observing? This is the representation of a C0 gate. Okay. So once again let me draw. So this is A. Okay. So and this is B. So here we have plus round like this. This is the representation we have to follow. This is the C0 gate representation. Okay. Now what he is asking is why that A is not connected something. Listen. I told you all quantum gates are reversible quantum gates. That's why in number of inputs and the number of outputs are same. There will be no change. This will be as it is A. and this operation for C naught, this is given by B modulo 2. I repeat, it's not XR. Okay, maybe in your maybe XR also we can say. I think in your digital electronics we call it as XR gate. So you remember XR gate? Okay, so this A. So wait a minute. Now see, this is the textbook's point of view. This is called modulo 2 addition. Modulo 2 addition, under addition. Sir, what is this modulo 2 addition? Wait a minute. This addition means 0 plus 1 is 1, 1 plus 0 is 1, but 1 plus 1 is 0. Right, let me write one more. Wait a minute. So 0 plus 0 is 0, but 1 plus 1 is equal to, actually you will get 2. Modulo 2 means we should not get 2. You have to divide that with 2, and whatever the remainder you are getting, you have to write. So that's why I think you know modulo operation, that's why it is 0. So are you ready now? Listen, everyone. So here I am taking the truth table. I think Krishna, you asked whether shall we write the truth table. Yeah, I am trying, just see. So this is AB inputs and output is A, and another output is B XR A. Something like this. Everyone, please observe. So whenever digital electronics we have two inputs, how you will write? 0 0, 1 0, 0 1 and 1 1. Okay. Now what sir said, this A will be as it is, no change. That controlled bit output is as it is. It will only control the target. Actually this is called a target. Let me give the names also. Target. And this is called a controlled bit. So why it is called a control bit? It will control the target. So this will be as it is, and this will control the value of target. So 0 XR 0, I am saying, okay, this is A as it is, 0, 0, 1, 0. Are you observing? Now B XR A, that means add this 0, add this 1, add this 1, add this 0. Yeah, please check. Sorry. What is this? 1. Now please check. So if 1 plus 1, here 0. 1 plus 0, 1. 0 plus 1, 1. So if you see this last two things, what happened? 1 0 become 1 1, 1 1 become 1 0. So what is a C0 operation? The C0 operation is, if you have 1 0 state, it will convert to 1 1, and 1 1 state is there, it will convert to 1 0. This is what I told you earlier. So what I explained, see that matrix. No need to do all these things. Just see that matrix. In that matrix, what are the changes occurs from identity matrix? Your third and fourth columns are interchanged. So third column stands for 2 number, fourth column stands for 3 number. So 2 and 3 are interchanged. In binary notation, 2 and 3 you know already. 2 means 1 0, 3 means 1 1. That's it. Is that clear? So this is about C0 gate. Okay, wait a minute. So introduction, I mean in the beginning I am giving like this, but we will solve some problems also, don't worry. Just wait a minute. Let me take the second one, you will understand. Everybody please. Now second one, I am taking U as a Z. That means 1 0 0 minus 1. Then what is my CU operation? This is I2, O2, O2 and Z. Everyone please listen. I 1 0 0 1 0 0 0 0 0 0 0 1 0 0 minus 1. Don't do anything. Just apply whatever the technique I told you. Please compare this with I. Compare with I, identity matrix. Just check. First column same, same. Second column same, same. Third column same, same. Fourth column same, no. So what happened? The fourth column is having a negative sign. That's why. Now can you please tell me what is this? 0, 1, 2, 3. So 3 become minus 3. That's it. What is 3? 1, 1. That will become minus 1, 1. That is the CZ gate. So this is what I am saying. No need to go for algebra because we are physics students and we know very well mathematics. So that's why what I am saying is whenever you have any quantum gate, just to compare with the identity matrix. And what are the changes occur from that identity matrix and see. This is valid for 3 qubit gates also, single qubit gates also, 2 qubit gates also. But I never read this point in any book. This is what I personally feel. That's what I'm saying. Okay. Maybe I'm wrong. I don't know. But at this time, till now, I got all the questions, all the answers, all the solutions I got by using this method. So that's it. So 1, 1 will become minus 1, 1. Okay. So the remaining states are as it is. Only this 1, 1 will become minus. This minus means what? Some phase. Now third one you please write. Take u is equal to s. What is s? 1, 0, 0, I. Then what will happen? 1, 0, 0, I. Now tell me what is that CS, C phase? Last column is changed. Last column is multiplied with iota. That's why 3. Last column means 3. 3 become I3. I into 3. That means 1, 1 become I into 1, 1. Can you write yourself the last one? Please try. Third one. Take u is equal to s. Then that is called C phase. S is nothing but 1, 0, 0 iota. Please write. Write yourself. Yes. Again doubt, Bob. I think your hand is still raised. Any doubt, Babu? Okay, okay. No problem. Please ask. But always my advice is don't see the things in a regular manner. Please see in a different manner. Whether you are right or wrong, time will decide, future will decide. First you have to get something, a different way, different thinking. But Krishna, I don't know whether we can frame the all the things like this. I'm not sure. Okay. Just here it is possible because XR gate, it is easy. That's why we have drawn this. So once we constructed the matrix, once we constructed the any quantum gate, it is represented by a unitary matrix. That unitary matrix definitely have some change from identity matrix. So my point is, in all the quantum gates, whatever the change occurs, the same change is nothing but the operation. This is what I want to convey. So this is 0, 0, 0 and 0, 0, 1. Please write along with me. 0, 1, 0. Don't copy this also because 1, 0, 0, 4, 1, 0, 1, 5, 1, 1, 0, 6, 1, 1, 7. This is 0 and this is 1. Value, that binary conversion, you know that already. 2, 3, this is for our convention I am writing 4, 5, 6 and 7. Okay, so as usual, you know this will form a I am not writing, but you know this will form a I8. Okay, it will become a big one. That's why I'm not writing. You know I8. 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, something like that. All diagonal elements are 1, 1. You can represent like this also. In mathematics, 1, 2, 3, 7. That is also the representation of I8. Okay, wait a minute. Are you ready? Single qubit quantum gates represented by e raised to I gamma Rn cap of theta. Two qubit quantum, this is U actually. Two qubit quantum gates, Cu. That means controlled U. So here we have I2, O, U. Whatever U is here, you are substituting here. Wait a minute. Next, this is a single qubit, this is a 2 qubit. Now 3 qubit, don't write. 3 qubit. This is a controlled U. We call it as a C square U. 2 qubit gates are controlled unitary. 3 qubits are controlled unitary. That means a C square U. So I hope you understand here what you will get. I4, O4, O4 and here Cu. You got it? Cu. Yo, I forgot to explain one 2 qubit quantum gate, that is swap gate. Okay, I will explain, don't worry. So that's it, and this is the form. Wait a minute, I forgot. Right. So okay, anyhow, these 3 qubit quantum gates are given by controlled. How many control bits are there? 2 control bits. 2 control bits are changing the value of the target. Controlled unitary. Earlier Cu, 1 control bit exists, that is controlling the value of target. Here 2 control bits are changing the value of target. So this is represented by controlled unitary. So which is a C square U. Everyone listen please. So here we have C1 controlled, C2 another controlled. You have to write this, you should not write this. I repeat, you should not write this. You have to write the dots only. And here target. Okay. And here you have the unitary operation. I hope you are listening. Maybe if you get bored, okay, you can leave. It's no issue, no problem. That's it. So the C1 is as usual and C2 is as usual, and this one is given by T XR C1 C2, something like that. This is a representation. Okay, so no need to worry, because here leave it. Yeah, so this is the C square U operation, which is given by I4 O4 and U4. Wait a minute, all of you please listen, Now here I have a choice to select U4. I'm sorry, by mistake I didn't explain one more 2 qubit gate. I forgot. I will explain. So I'm taking C0. Oh, Sir is taking that U4 is replaced by C0. The other thing I didn't explain, this is actually swap gate. You have two options. You can replace U with the C0, or you can replace U with the swap. I'll tell you what is a swap, don't worry, tension. If you replace with the C0, listen, don't write. In the class also writing, here also writing, Amma, listen first. C0. This is C0. If you replace U with the C0, this is called Toffoli gate, Fredkin gate. Wait a minute. So I got the confusion with the names. The two gate. Yeah, this is called Toffoli. And if you replace this U with the swap gate. Swap means that interchanging. This is called Fredkin gate. So So there are three qubit quantum gates. One is a Toffoli, another is a Fredkin. Because I didn't explain this, that's why you don't know about Fredkin. Just leave it and come to this Toffoli. So now you are taking U as a C0. Everyone, please listen. Then the Toffoli gate. The Toffoli gate is, I would like to write properly because you have to know what is the operation. Are you ready? 1 0 0. Wait. Yeah. 1 0 I4 0 0 0 1 0 0 0 0 1 0 0 0 0. Just write one time. Okay, so now C0. C0 means what? That second and third interchange. 1 0 0. Yeah. So that's it. And 0. So 1 0 0 0 0 1 0 0. Second and third are interchange 0 0 1 and 0 1 0. I hope you understand. That's it. Now everybody listen. Now just compare with I8. First, everyone, is it first row? Yes, sir. First column? Yes. Second column, that means 1. I hope you know 0, 1, 0, 1, 2, 3, 4, 5, like that. Is it 0? Yes. Is it 1? Yes. Is it 2? Yes. 3? Yes. 4? Yes. 5? Yes. Is it 6? No, it's a 7. Is it 7? No, it's a 6. That's it. I hope now you understand what a Toffoli gate is doing. It is it is interchanging 7 and 6. So the Toffoli operation 6 to 7, 7 to 6. Generally after doing the mathematics we have to write, but we are not doing. 6 means what? I think 1 1 0, 7 1 1 1. Now carefully see. What is C0 gate? First qubit is 1, then the second qubit is flipped. Now this is Toffoli gate. That means controlled NOT gate. Repeat, controlled NOT gate. So first two qubits are 1 1. First two qubits are 1 1. Then it is flipping the third qubit. So if first two qubits are 1, okay, then third qubit is flipped. Whatever you understand, you write in your own language. If first two qubits are equal to 1, then the third qubit is flipped. Otherwise, no change. So, Toffoli gate, no need to get tension. So, if you observe with the identity matrix, we have seen all these things are no change. Okay, the only change is 7 and 6. That's why whatever the technique we have done earlier, it is interchanging 6 and 7 number. In binary notation, 6 means 110, 7 means 111. So 110 change to 111 and 111 change to 110. So first two qubits are 1, then only third qubit will be flipped. First two qubits are equal to 1, then only third qubit will be flipped. In C0, first qubit is 1, second qubit will be flipped. Got it? Come on, I will explain this both. Very easy to understand, not at all difficult. Very good thing is no integration, no differentiation till now. So what a Toffoli operation? The Toffoli operation is 6 and 7 are interchanged. 6 converted to 7, 7 converted to 6.